Graphs of polynomial functions. The revenue in millions of dollars for a fictional cable company from 2006 to 2013 is shown in Table 1. The revenue can be modeled by the polynomial function r of t equals negative 0.037 t to the fourth power plus 1.414 t to the third power minus 19.777 t to the second power plus 118.696 t minus 205.332, where r represents the revenue in millions of dollars and t represents the year. With t equals 6 corresponding to 2006, over which intervals is the revenue for the company increasing? Over which intervals is the revenue for the company decreasing? These questions, along with many others, can be answered by examining the graph of the polynomial function. We have already explored the local behavior of quadratics, a special case of polynomials. In this section, we will explore the local behavior of polynomials in general, recognizing characteristics of graphs of polynomial functions. Polynomial functions of degree 2 or more have graphs that do not have sharp corners. Recall that these types of graphs are called smooth curves. Polynomial functions also display graphs that have no breaks. Curves with no breaks are called continuous. Figure 1 shows a graph that represents a polynomial function and a graph that represents a function that is not polynomial. Using factoring to find zeros of polynomial functions. Recall that if f is a polynomial function, the values of x for which f of x equals 0 are called zeros of f. If the equation of the polynomial function can be factored, we can set each factor equal to 0 and solve for the zeros. We can use this method to find x-intercepts because at the x-intercepts we find the input values when the output value is 0. For general polynomials, this can be a challenging prospect. While quadratics can be solved using the relatively simple quadratic formula, the corresponding formulas for cubic and fourth degree polynomials are not simple enough to remember, and formulas do not exist for general higher degree polynomials. Consequently, we will limit ourselves to 3 cases. 1, the polynomial can be factored using known methods, greatest common factor and trinomial factoring. 2, the polynomial is given in factored form. 3, technology is used to determine the intercepts. Identifying zeros and their multiplicities. Graphs behave differently at various x-intercepts. Sometimes the graph will cross over the horizontal axis at an intercept. Other times the graph will touch the horizontal axis and bounce off. Suppose, for example, we graph the function shown, f of x equals x plus 3 multiplied by x minus 2 squared multiplied by x plus 1 cubed. Notice in figure 7 that the behavior of the function at each of the x-intercepts is different. The x-intercept, x equals negative 3, is the solution of the equation x plus 3 equals 0. The graph passes directly through the x-intercept at x equals negative 3. The factor is linear, has a degree of 1, so the behavior near the intercept is like that of a line. It passes directly through the intercept. We call this a single zero because the zero corresponds to a single factor of the function. The x-intercept, x equals 2, is the repeated solution of the equation x minus 2 squared equals 0. The graph touches the axis at the intercept and changes direction. The factor is quadratic, degree 2. So the behavior near the intercept is like that of a quadratic. It bounces off of the horizontal axis at the intercept. X minus 2 squared equals x minus 2 multiplied by x minus 2. The factor is repeated, that is, the factor x minus 2 appears twice. The number of times a given factor appears in the factored form of the equation of a polynomial is called the multiplicity. The zero associated with this factor, x equals 2, has multiplicity 2 because the factor x minus 2 occurs twice. The x-intercept, x equals negative 1, is the repeated solution of factor x plus 1 cubed equals 0. The graph passes through the axis at the intercept but flattens out a bit first. This factor is cubic, degree 3, so the behavior near the intercept is like that of a cubic with the same shape S shape near the intercept as the toolkit function f of x equals x cubed. We call this a triple zero, or a zero with multiplicity 3. For zeros with even multiplicities, the graphs touch or are tangent to the x-axis. For zeros with odd multiplicities, the graphs cross or intersect intersect the x-axis. See Figure 8 for examples of graphs of polynomial functions with multiplicity 1, 2, and 3. For higher even powers, such as 4, 6, and 8, the graph will still touch and bounce off of the horizontal axis, but for each increasing even power, the graph will appear flatter as it approaches and leaves the x-axis. Graph behavior. For higher odd powers, such as 5, 7, and 9, the graph will still cross through the horizontal axis, but for each increasing odd power, the graph will appear flatter as it approaches and leaves the x-axis. Graphical behavior of polynomials at x-intercepts. If a polynomial contains a factor of the form x minus h raised to the p power, the behavior near the x-intercept h is determined by the power p. And we say that x equals h is a non-zero of multiplicity p. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. The graph will cross the x-axis at zeros with odd multiplicities. The sum of the multiplicities is the degree of the polynomial function. Determining end behavior. As we have already learned, the behavior of a graph of a polynomial function of the form f of x equals a sub n, x raised to the nth power, plus a sub n minus 1, x raised to the n minus 1 power, plus, and so on, plus a sub 1x plus a sub 0 will either ultimately rise or fall as x increases without bound, and will either rise or fall as x decreases without bound. This is because for very large inputs, say 100 or 1000, the leading term dominates the size of the output. The same is true for very small inputs, say negative 100 or negative 1000. Recall that we call this behavior the end behavior of a function. And as we pointed out when discussing quadratic equations, when the leading term of a polynomial function, a sub n, x to the nth power, is an even power function, as x increases or decreases without bound, f of x increases without bound. When the leading term is an odd power function, as x decreases without bound, f of x also decreases without bound, and as x increases without bound, f of x also increases without bound. If the leading term is negative, it will change the direction of the end behavior. Figure 11 summarizes all four cases. Understanding the relationship between degree and turning points. In addition to the end behavior, recall that we can analyze a polynomial function's local behavior. It may have a turning point where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. Look at the graph of the polynomial function. F of x equals x to the fourth power minus x cubed minus 4x squared plus 4x in figure 12. The graph has three turning points. This function, f, is a fourth degree polynomial function and has three turning points. The maximum number of turning points of a polynomial function is always one less than the degree of the function. Interpreting turning points. A turning point is a point of the graph where the graph changes from increasing to decreasing, rising to falling, or decreasing to increasing, falling to rising. A polynomial of degree n will have at most n minus 1 turning points. Graphing polynomial functions. We can use what we have learned about multiplicities and behavior and turning points to sketch graphs of polynomial functions. Let us put this all together and look at the steps required to graph polynomial functions. Using the intermediate value theorem, in some situations we may know 2 points on a graph but not the zeros. If those 2 points are on opposite sides of the x-axis, we can confirm that there is a zero between them. Consider a polynomial function, f, whose graph is smooth and continuous. The intermediate value theorem states that for two numbers, a and b, in the domain of f, if a is less than b and f of a does not equal f of b, then the function f takes on every value between f of a and f of b. While the theorem is intuitive, the proof is actually quite complicated and requires higher mathematics. We can apply this theorem to a special case that is useful in graphing polynomial functions. If a point on the graph of the continuous function f at x equals a lies above the x-axis and another point at x equals b lies below the x-axis, there must exist a third point between x equals a and x equals b where the graph crosses the x-axis. Call this point C, f of c. This means that we are assured there is a solution C where f of c equals 0. In other words, the intermediate value theorem tells us that when a polynomial function changes from a negative value to a positive value, the function must cross the x-axis. Figure 17 shows that there is a 0 between a and b. Intermediate value theorem, let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value, c, between a and b for which f of c equals 0. Writing formulas for polynomial functions. Now that we know how to find zeros of polynomial functions, we can use them to write formulas based on graphs. Because a polynomial function written in factored form will have an x-intercept where each factor is equal to 0, we can form a function that will pass through a set of x-intercepts by introducing a corresponding set of factors. Using local and global extrema, with quadratics, we were able to algebraically find the maximum or minimum value of the function by finding the vertex. For general polynomials, finding these turning points is not possible without more advanced techniques from calculus. Even then, finding where extrema occur can still be algebraically challenging. For now, we will estimate the locations of turning points using technology to generate a graph. Each turning point represents a local minimum or maximum. Sometimes a turning point is the highest or lowest point on the entire graph. In these cases, we say that the turning point is a global maximum or a global minimum. These are also referred to as the absolute maximum and absolute minimum values of the function. Local and global extrema. A local maximum and local minimum at x equals a, sometimes called the relative maximum or minimum, respectively, is the output at the highest or lowest point on the graph in an open interval around x equals a. If a function has a local maximum at a, then f of a is greater than or equal to f of x for all x in an open interval around x equals a. If a function has a local minimum at a, then f of a is less than or equal to f of x for all x in an open interval around x equals a. A global maximum and global minimum is the output at the highest or lowest point of the function. If a function has a global maximum at a, then f of a is greater than or equal to f of x for all x. If a function has a global minimum at a, then f of a is less than or equal to f of x for all x. And we can see that the difference between local and global extrema in figure 21. Dividing polynomials. The exterior of the Lincoln Memorial in Washington, D.C. is a large rectangular solid with length 61.5 meters, width 40 meters, and height 30 meters. We can easily find the volume using elementary geometry. As we can confirm from the dimensions above, the height is 30 meters. We can use similar methods to find any of the missing dimensions, and we can also use the same method if any or all of the measurements contain variable expressions. For example, suppose the volume of a rectangular solid is given by the polynomial 3x fourths minus 3x cubed minus 33x squared plus 54x. The length of the solid is given by 3x, the width is given by x minus 2. To find the height of the solid, we can use polynomial division, which is the focus of this section. Using long division to divide polynomials. We are familiar with the long division algorithm for ordinary arithmetic. We begin by dividing into the digits of the dividend that have the greatest place value, and we divide, multiply, subtract, and include the digit in the next place value position and repeat. For example, let's divide 178 by 3 using long division. Another way to look at the solution is a sum of parts, and this should look familiar since it is the same method used to check division in elementary arithmetic. And we call this the division algorithm. And We will discuss it more formally after looking at an example. Division of polynomials that contain more than one term has similarities to long division of whole numbers. We can write a polynomial dividend as the product of the divisor and the quotient added to the remainder. The terms of the polynomial division correspond to the digits and place values of the whole number division. This method allows us to divide two polynomials. For example, if we were to divide 2x cubed minus 3x squared plus 4x plus 5 by x plus 2, using the long division algorithm, we can identify the dividend, the divisor, the quotient, and the remainder. The division algorithm. The division algorithm states that given a polynomial divided dividend f of x and a non-zero polynomial divisor d of x, where the degree of d of x is less than or equal to the degree of f of x, there exists unique polynomials q of x and r of x such that f of x equals d of x multiplied by q of x plus r of x. Q of x is the quotient and r of x is the remainder. The remainder is either equal to 0 or has degree strictly less than d of x. If r of x equals 0, then d of x divides evenly into f of x. This means that in this case, both d of x and q of x are factors of f of x. Using synthetic division to divide polynomials. As we've seen, long division of polynomials can involve many steps and be quite cumbersome. Synthetic division is a shorthand method of dividing polynomials for the special case of dividing by a linear factor whose leading coefficient is 1. Synthetic division is a shortcut that can be used when the divisor is a binomial in the form x minus k, where k is a real number. In synthetic division, only the coefficients are used in the division process. Using polynomial division to solve application problems. Polynomial division can be used to solve a variety of application problems involving expressions for area and volume. We looked at an application at the beginning of this section. Now we will solve that problem in the following example. Example 6, using polynomial division in an application problem. The volume of a rectangular solid is given by the polynomial 3x fourth minus 3x cubed minus 33x squared plus 54x. The length of the solid is given by 3x and the width is given by x minus 2. Find the height t of the solid. Access these online resources for additional instructions and practice with polynomial division. Dividing a trinomial by a binomial using long division. Dividing a polynomial by a binomial using long division. Dividing a polynomial by a binomial using synthetic division. And example 4, dividing a polynomial by a binomial using synthetic division. openstackscollege.org